Hello, um, welcome. Good morning, all of you. Uh, my name is Atre. Um, uh, I'm a NASA postdoctoral fellow at NASA Marshall Space Flight Center. Um, uh, on behalf of Let's Talk Astronomy team, I welcome you all for this session. In this session, the schedule would be we have a daytime astronomy followed by some question and answer session, followed by nighttime astronomy, and then we'll have some question and answer session. At the end of it, we would discuss the overview of career options in astronomy and astrophysics. We'll take up all the question and answers during that time as well. So again, we know that we are all meeting here because the entire world has come to a status where we need to adapt and adjust to the new way of normal life where we are staying indoors. So due to the COVID-19 pandemic. So however, these challenging times should not stop us from learning something new to keep us active to keep our scientific temper as well as the engineering knowledge. So therefore, some of us who are working in different fields of astronomy and astrophysics would like to engage and motivate our Indian student community to discuss some of the scientific aspects of astronomy and share our experiences. So in this, we plan to present a very broad overview of astronomy and discuss some of the challenges involved. At the end of the session, we will also discuss some of the possible career options which are available to pursue to have to pursue in astronomy. So we strongly encourage you to make use of this and make the most of your time here and get actively involved with the question and answer session. And once again, on behalf of Let's Talk Astronomy team, I welcome you all for the session. So in this, who are we? Many of you might have gone through our web pages. So if you have not, I strongly encourage you to visit our webpage. So we people are PhD students and postdoctoral associates from working at various institutes. We are all Indian citizens, but we are working at various institutes across the globe. So you can see them here. So some of us are solar physicists, planetary scientists, instrumentation experts, and also people do various parts of astronomy and astrophysics, galaxy, cosmology, and whatnot, everything. So in this session, so we would like to give a brief overview. There are two parts. One is the day and one is night. So in the day part, we will discuss something interesting facts about the sun, or one of the most observed objects in the daytime. And we will talk about some of the interesting questions which are still not solved. And we will also discuss what are all the challenges involved, briefly touch upon the challenges and some of the observatories which are used to do that, to understand that. And in a similar way, we also look at the night sky, so where you have stars, planets, and understanding the universe, cosmology. So all those, we would give a very nice overview of that, and then discuss some of the unsolved questions combined with what are all the challenges involved in doing these observations and studies. So in this, as I mentioned before, so here we have we'll start with the daytime astronomy and discuss about around 25 minutes. And then we'll take up some question and answers for the daytime. And I would strongly encourage you to ask a lot of questions. And again, after which we will take up some questions and then we'll go to the nighttime astronomy. Don't get discouraged if it is not answered immediately. We will answer all your questions throughout this session. If not, we will keep you posted in our webpage, your questions as well as with the answers. So in the nighttime astronomy, we'll take another half an hour and then take up the questions, followed by an overview of possible career options, what one can do by pursuing astronomy, or to pursue astronomy as a research career. So after which we will take up the question and answers again in terms of career as well as the overall astronomy session before we conclude. So again, I want to remind you, so the way to ask questions. So most of you are aware, but just wanted to repeat it. So you can ask questions by going to our webpage where there is a click here to ask questions and follow the link. So where you have, please put your name, email address, and then give questions in the corresponding section, daytime, nighttime, or career related. And we also welcome your feedback and constructive comments on this so that we can improve that. And if you want, you can also access the question page by going through below your YouTube channel where we have the question link, which is there. So you can use that. So put your uh, questions in the question box. And again, I once again welcome you all for this session, and please make use the best use of it. And we'd be happy to share our experiences. So on the first session would be on the daytime astronomy, which I would be taking for today. So let's start with daytime astronomy. Again, welcome you all for the daytime astronomy. Okay, what is daytime astronomy? So one of the most interesting object or observed object in the daytime sky is the sun, which we all know, which is the closest star. So we are in the first 20 minutes, 25 minutes, we are going to discuss about the sun and some of the interesting facts and some of the unsolved questions which we have, and why we need to study and how we are studying. So all those aspects we'll be talking today. Yeah, the interesting question, why do we need to study the sun? Yes, we know that our whole life on Earth is sustained because of the presence of our star, the sun. So because we are taking light, we take heat, and we take energy from the sun in all forms. So not only that, our biological, the diurnal cycle, so our sleeping patterns, everything is associated, the day and night, is associated with the presence of sun. Not only that, so agriculture, so kind of seasons which we are talking. So as you can see in this image where we have summer, spring, winter, and autumn. So all these beautiful seasons, though it is due to the tilt of Earth, but its sun plays a major role in contributing to the seasons. So we need to understand how, at least to some extent, we have some understanding, and we need to further understand about the sun. So this is a reason for that, because it is everything for us. Second, why do we need to study the sun? So to answer this, another answer is a sun is not the only star in the universe. So there are billions of stars in our Milky Way. You have the image of the Milky Way here, where sun is just a tiny dot in one of the spiral arms. And this is the closest star we have, which I already mentioned, that with a distance of around 150 million kilometers from Earth. So that since there are billions of stars, if you want to understand how stars are formed, how do they evolve, how do they die, so to understand all these things, sun is the best way to understand that, because it's the gateway, it's the closest object for us, it's a study object for us to do that. So that's another reason why we need to study our sun. Yes, this is interesting. Sun could also be dangerous. So that's one of the reasons why we need to study the sun. So why it is dangerous, I'll talk about it as we move along in this presentation, because there are a lot of harmful radiations, charged particles, X-rays, gamma rays, which all come from sun. So that is another reason why we need to understand that, why it is coming. So we've discussed about that here. So why it is dangerous, we will talk about this. So to start with, what is the structure of the sun? So as you know that the sun is a star. So, but if you think of sun, so you can talk, it's a hot ball of gas, okay? But it has different structures similar to what you have an onion structure. So every time if you peel, you will find some other structure inside. But every structure every layer of the structure is totally different from each other, and everyone plays an important role in transferring the energy that ultimately the sun emits. So in this picture, you can see different layers of the sun which are marked. So you can see the core, you can see different layers like photosphere, chromosphere. So we'll talk about it. So um, uh, the first part is the core. So core is the centralmost part of the sun, where the temperature is 15 million Kelvin. So it's 15 million Kelvin. So a very high temperature with high density, where it's mostly filled with the hydrogen nuclei, where the fusion reaction happens that provides the energy for the sun. So that, to compare, our human body temperature is around 300 Kelvin, and even the molten lava from volcanoes, that the temperature is around 1000 to 1500 Kelvin, whereas compare the temperature which we are talking in core, which is 15 million Kelvin, so which is very high temperature. So which is the reason why how these overcome all the forces and then make these reactions to happen, where four hydrogen nuclei, they fuse to give out helium and a set of radiation and neutrinos, and this is the sole energy of the sun which is happening inside the core. Now, after this, the radiation which is coming from this nuclear reaction, so that comes out, and then as we all know that the energy can be transported through radiation, conduction, and convection. So the first part of the layer is the radiation zone, where the energy transport, the heat transfer, is happening um, via radiation. And the radiation, as I told you, that the core is 15 million Kelvin, the temperature when you reach the radiation zone end of it, so it is 2 million Kelvin. And the next layer of the sun, which is here in the yellow marked here, so that's the convection zone, which is, what is convection? So you can think of boiling water where the bubbles are coming up and going up and down. So that is the transportation by convection. So the temperature at the base of the convection, which is the upper layer of the radiation zone, which is 2 million Kelvin. And the end of it, you have the surface, which is at 5700 Kelvin. So that's the visible surface which we see, which we call it the photosphere. So the photosphere is the surface where you can see the convection things happening, and that is the visible surface where the light coming from sun, the visible light coming from the sun, is what we see. So that the temperature is around 5700 Kelvin. Now, as I mentioned, that this is the layer where the convection is happening. That means when you try to look at sun, again, I want to tell you, I want to warn you, never ever look at sun directly with your naked eye, which I'll also be putting out some slides for that, but here I wanted to mention. So you cannot see that directly when you look at sun. So when you look at sun with a very high resolution telescopes, what you are expected to see is these convection motion. So that confirms this. That's how decades and centuries of observation people have made to understand how these layers are made of. So what I'm showing here is the latest high resolution telescope which we have, which is the Daniel Inouye Solar Telescope. It's a decist. So you can see that this is what the image obtained from looking at sun with this high resolution, ultra high resolution telescope. You can see the photosphere where the convection motion, the granulations are clearly observed. So scientists and people try to understand, look at these data from time to time, and then understand various properties of the solar atmosphere. Now, next layer is the chromosphere. So as you can see in this image, it's not easy to distinguish from other photosphere. It's for the same reason. It's for the simple reason that the chromosphere is very relatively less dense, and it is like the photosphere gives you enormous amount of light, which is like imagine like a sodium vapor lamp. In front of it, you have a small tiny candle or an LED bulb. So if you want to look at the light coming from the LED bulb, that means you need to block the light coming from the background or the bright source. So the photosphere is masking the light coming from the chromosphere. Then what is the way to study it? The natural way, the best way people have looked at it, or people got to know about this, is during the eclipse, solar eclipse. So where the moon, earth, and the sun, so they're all in the straight line, so which where the apparent the angular size of the moon fills the diameter of the sun, so that uh, blocks the radiation coming from the disk, which we call the photosphere. So that time you would be able to see the outermost layers or the interesting features of the solar atmosphere, which are the chromosphere. So that's how people started to understand this layer. And I would also show you some of the images, then people how people try to understand that it extends up to 2100 kilometers, and what how the temperature of this region, which is we have seen that the photosphere is at 5700 Kelvin, after which the temperature starts to come down, but after a certain point, then the temperature again starts to increase, which is going up to 8000 Kelvin. So uh, the last part of the layer of the sun, or the outermost atmosphere of the sun, is called the solar corona. So don't compare this with the coronavirus which we have, for which thanks to that we are all here to discuss about this. Um, um, this region extends beyond the interplanetary region. So the temperatures in this region goes from 1 megakelvin or 1 million Kelvin up to 20 million Kelvin. It's a puzzling thing. So you have a candle where the source is, but the temperature should decrease as you move away from the source. Whereas here it is decreasing until photosphere, but after chromosphere, then again the temperature starts to increase, which is a puzzling thing. So what's again, I want to give a recap that the core is 15 million Kelvin. Now I'm saying the corona, which is the outermost layer, that also glows in 1 million to 20 million Kelvin. So the reason why it is happening at the corona is, or how the corona is heated, is a $1 million question, which still people are trying to understand. And again, this region is also visible only during eclipse. So this is one of the greatest images which we have from the recent American eclipse in 2017. You can see the disk light is blocked by the moon, which is the black region, and you can see the beautiful outermost layers like the prominences and the magnetic field structures are clearly observed during this eclipse. So now, having seen all the multiple layers of solar atmosphere and solar interior, so did you notice that we also showed you some of the dark spots on the sun? So these are called the sunspots. So these are relatively cooler regions on the solar atmosphere, in the photosphere, to be precise. So we know that the photosphere is at 5700 Kelvin, and whereas these regions are going to be relatively cooler than what the other surrounding regions. So um, these are all the temperatures which we discussed. So what's exactly happening to this inside the sun? So we know that the sun is a ball, hot ball of gas. So now the gas which is there inside, and as we have seen that the temperatures are varying from so many megakelvins. So when you put solids and liquids and gas into different temperatures, so they change their phases. So at very high temperatures, which we are discussing as in the sun, so that the atoms would be in the plasma state, which is nothing but the fourth state of matter, where the electrons and protons would be essentially ripped off. So they would not be combined as a form of atom. So these electrons and protons, which are charged particles, as you know from your fundamental physics science class. So these are protons are positively charged and electrons are negatively charged. So the motion of these charges would create an electric field, and this electric field, along with the motions, then that induces magnetic field. That's how the magnetic field is generated. So as I said, that now sun is a hot ball of gas. It's not only ball of gas, it's a magnetized plasma. The sun is a hot magnetized plasma or ionized plasma. So that motion induces a magnetic field, and that is what is shown here. So sun is a strong magnetic field of 1000 to 4000 Gauss. So to have a comparison, what we have on Earth is just zero point 0.5 Gauss, whereas what we have on our the laboratory bar magnets, we have an average of 100 Gauss. You compare this, it's 10 times very strong magnetic field than what we have. So what happens? The sun, as I said, it's a hot gas, ball of gas. So when it rotates about its axis, the magnetic field, it is rotating in such a way that the it is moving faster at the equator compared to what it is moving in the poles. It is rotating in the poles. So this would stretch the magnetic field moving along the equator. So it's like a rubber band. So it's just pulling those magnetic field lines along with it, along with the motion, because the plasma is moving along with that. So that motion eventually gives you a lot of features which you see on the solar atmosphere, or essentially the photosphere. And this is one of the manifestation is what the sunspot is. This is a typically magnetically active region and relatively cooler region compared to the surroundings. That's why you see this dark compared to the surroundings on the photosphere. And again, the fact here is the sunspots are typically bigger than size of the Earth. So they vary from size. They vary from large range of sizes of sunspots, which you see on the solar disk. And I also want to mention that these sunspots, they appear on this solar disk, and where people track how many spots are there on, you can see on the solar disk, and then plot it as a function of days, and that shows a change. The sunspot changes with time, it increases, and then again the sunspot number decreases. And this with centuries of observation, people have seen or have come up with that study that there is a 11-year cycle where the sunspot increases and decreases. So some of the other manifestations of these magnetic fields, so we know that from various observations, we have very interesting phenomena like filaments, prominences. These are all different emissions which are caused by these change in the magnetic field structures on the topology on the solar atmosphere. So solar flare, eruptions, and coronal mass ejection. These are all often, you might have heard in many movies or many places where solar tsunami, solar eruptions, Earth is going to get affected. These are all nothing but these magnetic activity on the solar atmosphere. They are coupled and they release enormous amount of charged particles and X-rays, gamma rays, and high energy particles like protons, heavy ions. Everything would be spilled into the interplanetary space. As you can clearly see, one of the images, this is one of the beautiful images taken from NASA. So you can see from HAO, so where you can clearly see the eruptions are happening at various various scales. And the image here is what the coronagraph. What we do is, I mentioned to you that to observe the other regions of the atmosphere, you need to block the light coming from the photosphere. And the blue region here is blocking the light coming from the sun. This is from LASCO. It's a coronagraph observatory on board SOHO. And all these beautiful emissions, the ejections, coronal mass ejection coming out from the sun is clearly visible because we blocked the light coming from the photosphere. This is called the experiment called coronagraph. So how much energy is released? You can see that their energies are 10 power 20 to 25 joules. It's just a number, but when you want to relate it, it is equivalent to millions of 100 megaton hydrogen bombs. Imagine such a powerful source we have near to us. And why does it matters? Because as I said, that it gives you charged particle X-rays and gamma rays, and it is throwing out everything into the interplanetary space, and all of us are sitting here. So though we know that our Earth protects us, but these charged particles, they come to Earth and then they precipitate along the polar regions. So these producers called the aurorae borealis and australis on the northern and southern regions, where the charged particles induce emissions in the atmosphere of Earth. This is very important. We may not be able to see in India because we are close to the equatorial zone, but this is very evident in the polar regions. And also, this is an important topic which is called the space weather, because these charged particles are going to affect all our satellites, all our manned space program, astronaut space program, all of them, people who are going outside. So they all have to be protected. Otherwise, you get attacked by these radiation coming from the sun. Also, the signals which we are getting, these days we use GPS and internet very often. So it's a part of our life. So these satellites would get affected because of that. How did we learn all this? Again, I wanted to say, don't ever look at sun with your naked eyes. So as we know that if you want to study your interior part like bones, so then you go study with x-rays like the dental x-rays or chest x-rays. When you want to look at a people like visible wavelength where the light is getting reflected. When you want to look at people in thermal mapping, where you use our body temperature, which glows in infrared. So by looking at the same person in different wavelengths, you study different features in a similar fashion. So you also study the sun with the different wavelengths. Again, I want to emphasize the sun is the source of all energy that it gives you. It gives radiation from X-rays and gamma rays to radio waves. So when light goes into the prism, many of you might have done this experiment or have seen this experiment, and visible light goes into that, and then it gets spread into 7 colors in the visible colors which we see. Similarly, you have a spectrum coming in all the wavelengths in the electromagnetic spectrum, and what we see on the earth is only a part of the spectrum because the earth's atmosphere blocks it, whereas we do have wavelengths and covering all these. These are all some of the beautiful images of the sun in multiple wavelengths, as you can see. Again, don't look at sun with your naked eye. Use the protective gears. So how these multi-wavelength studies are generally observed. So people do have ground-based telescopes, and people do have space-based telescope, NASA, European Space Agency, JAXA, Indian Space Research Organization. So there are a lot of interesting space observatories which we have, and there are interesting observations from balloon experiments, and there are experiments from aeroplanes as well as from sounding rockets to observe the sun. So to give a glimpse of what are all the observational facilities in India, we do have Udaipur Solar Observatory in Rajasthan, which observes the sun in optical wavelengths. And we have Gauribudhanur Observatory in Karnataka, which does observations in radio. And we do have Kodaikanal Solar Observatory, which is one of the oldest solar observatory in India. So, and this is there in Tamil Nadu. So Kodaikanal Solar Observatory has various suites of experiments which observes the sun in multiple wavelengths, as I said, and each one has a dedicated role in observing some of the scientific questions of the sun. So, and I encourage you to visit the web page, and the data coming from, it's 100 years of data, more than 100 years of data, which is available online. So you can have a look at it. If you want, you can take some project on working about this Kodaikanal Solar Observatory data, which is, I welcome you all to have a look at this web page and utilize this. And to end the talk, so I would like to say that India is also going to launch a space dedicated solar observatory or solar mission called Aditya, which is going to be placed at Lagrangian point L1. So which is the point between the sun and the earth where the gravitational forces balance each other, and which is this mission is going to carry suites of 7 experiments to observe the sun in multiple wavelength, and this is scheduled to launch by the end of 2021. So with this, I will stop here. So because I've covered how various aspects of the sun, so I would, if you have any questions, and please follow the link and give your questions. I will be able to answer. Thank you.
Thank you for that informative talk, Atre.
Yeah.
And we would like to encourage the students to ask questions about the sun and the solar system right now, so that we'll be able to answer your questions. Anything about the talk or anything in general about the sun that you guys wanted to ask us about. So you can key in your questions right now. So while we are getting questions, let me ask a few that we already have, which the students posted while you were giving a talk, Atre.
Mhm.
So the first question is by Akash, and this question is to Soumya. What's the temperature of the sunspot, and why does the temperature of the chromosphere and corona increase? Soumya?
Yeah. Hi, Akash. Yeah, so thank you for these questions. They are very important questions. So the first question that you ask is what is the temperature of the sunspot? So as Atreya mentioned, the surface temperature of the sun is around 6,000 Kelvin, and sunspots are relatively cooler structures. So on an average, they are about 1,000 to 2,000 Kelvin cooler than the surrounding photosphere, which is the visible surface. And the second question that you ask is what is the reason for corona and chromospheric heating? It's a very important question that people are still trying to answer. We don't know the exact answer yet, but people have proposed some ideas that magnetic fields are interacting. Sun is a magnetized ball of plasma, as Atreya said. So there is magnetic field in the chromosphere and in the corona. So magnetic fields in different structures are interacting and they are leading to phenomena called magnetic reconnections. And then in structures which have magnetic fields, there are some movements because of which waves are generated. So there are many theories which say which propose different mechanisms for this heating. All of them are in one way or the other related to magnetic field. So we believe that magnetic field is responsible for this heating, but the exact mechanism and how this happens is not yet known. So this is one of the important questions that scientists are still trying to find an answer for. Yeah.
Thank you, Soumya. That was a nice answer. In fact, that is one of the most important questions that we guys face in solar physics. And if someone finds an answer, that would be, like Atre told, $1 million question that's been answered. We may even get a Nobel Prize. Okay, so the next question is by Piyush Raj. And this question is to Varun. In one of the slides that Atre showed, he talked about the Lagrangian point 1. So what is L1 point, and why is it used for solar observations?
Yeah. Am I audible?
Yes.
Okay. So hi Piyush. In fact, every time whenever we talk about the solar mission, we get this L1 point question. So yeah. So here is the answer your question. The Lagrange point is a location in space where the combined gravitational forces of two large bodies, in our case it is Earth and Sun, almost equals. And these are also called as parking place in the space, where you can you can go and park your vehicle like that. So which means satellite uses very minimal fuel to retain its orbital position. You know that whenever satellite is there in the space, so it has to rotate, so it has to use the fuel. So this at this place they use very minimal fuel exactly. And there are 5 such points named as L1, L2, L3, L4, and L5, where these kind of where this gravitational force almost equals actually, and that L1 and L2 are the nearest to us. And L1 is mainly used for the solar radiation because L1 point affords an uninterrupted view of the sun. Like Earth does not come into the picture over there, or rather, Earth or Moon does not obstruct the sun viewing. So if we are at L1 point, we will be directly seeing sun without any interruption. I hope this answers your question, Piyush.
Thank you, Varun. So in fact, India's mission called Aditya L1 does the same thing. So it's going to park the satellite at L1 to observe the sun. Okay, let's move to the next question by Mayank. And this is for Samyuday. So how big is the sun relative to other stars?
Thanks for forwarding the questions, Mohan. And that's a good question, Mayank. So a sun is basically a very small star. It's called a yellow dwarf star, or if I get too technical, it's a G2V type star, which is the spectral classification of the sun. Now, the sun is basically in the main sequence. It's in a phase where it is converting hydrogen to helium. Now, there can be other stars who have evolved from this phase in their life cycle, and they could be, much larger than the sun, or there can be stars which are still converting their hydrogen to helium, that can be sort of massive, or as well as larger as compared to the sun. They can have a radius of, say, of uh, a few to 10 of solar mass. And uh, the stars that I'm talking about, where they have moved to the other phases of evolution, like a red giant brown star or an AGB stars, they can be few tenths of the size of the sun, few tenths of the solar radius. And then there are the supergiant stars, uh, which can have a radius of, say, 50 to few hundred of solar radius. So there can be stars which are, much, much larger in size than the sun. I hope that answers your question. Thank you.
Thank you, Sam. So the next question is for Shubham. If Shubham is okay with this, I'll be combining two questions for him. One is by Athira. So how much mass does the sun occupy in the solar system? And what is the closest star to the sun? And do stars affect us? So Shubham.
Yeah, hi. Yeah, those are good questions. So, as far as the mass of the sun is concerned, the solar system mass is almost entirely dominated by the mass of the sun. And the sun has a mass of something like 10 to the 30 kilograms, which is a million times higher than the mass of the Earth. The object that comes next is Jupiter, and Jupiter itself is roughly 1,000 times less massive than the sun. So most of the solar system mass is dominated by the star. And as for the other question about the nearest stars, well, the nearest star to the sun is Proxima Centauri, which is part of a triple star system. And this is around 4 light years away, which so the ratio between the distance to the nearest star and the distance to the Earth is the same ratio as 4 years to 8 minutes, which is quite a big number, as you can imagine. And as far as the effect of stars are concerned, it could be hazardous if a very nearby star explodes in a supernova explosion, in which case life on the planet could be threatened. But apart from that, the stars don't really affect us in a harmful manner. Thanks.
Thank you, Shubham. In fact, we really don't have any really threatening stars close to us that will go supernova and cause an extinction, if I'm not wrong. And the next question is for Krishna. And this question is asked by Manasa. What state is the chromosphere in? Since its temperature is so high, but the pressure is low, it can't be plasma. Is it a liquid or is it in its gaseous form? Krishna, can you answer that?
Yeah. Hi, Manasa. It's a nice question. So as you correctly pointed out, the temperature is quite high in chromosphere. It's tens of thousands of Kelvin, depending on what part of chromosphere you look at. But pressure is low, and compared to, of course, the pressure compared to the densities on the photosphere, so it is quite low. But still, because of the temperature, which is tens of thousands of Kelvin, it is partly ionized. It's not completely 100% ionized, which means to say that there are part of its mass is in neutral state, not ionized state, and it could be, depending on where you look at, there could be molecules as well. Still, we cannot call it liquid state. Maybe perhaps you can call partly gaseous state. Yeah, that's all. Thanks.
Thank you, Krishna. So the next question is for Sajal. Why is sunspot cooler? Sajal, can you take that question?
Yes. Yeah. So you heard that sun is a gaseous object. So the surface temperature is around 6,000, like 5,700 Kelvin. But there is some region on the sun photosphere, it's called sunspot, which is appears as a dark. That means that region is having strong magnetic field. So this strong magnetic field in such a way that it does not allow or inhibit the gas below the sunspot to hit the photosphere. So because of that, this region has little cooler temperature, and as it is have little less temperature compared to the surrounding, it appears as a dark. So main reason is that the strong magnetic field on the sunspot does not inhibit the hot gas to hit the photosphere. That's why it appears as a cooler.
Thank you, Sajal. Okay, so the next question is for Krishna again, and it's by Abhimanyu. So why does the sun's magnetic field flip, and how often does it flip? So this is basically the sunspot cycle that he's trying to ask.
Yeah. Hi, Abhimanyu. Good question. So the first I'll ask the second part, how often the sunspot's magnetic field flip? It flips every 11 years. So the North Pole becomes south and the South Pole becomes north. So why does it flip? It has something to do with the differential rotation. If you have seen some of the slides presented by Atre, so and also the other forces acting on it because of these motions. So here in the slide, you can see the differential rotation, the equators move faster and the polar regions move slower. So that is also the reason why sunspots form. So there will be small polarities of positive and negative patches on the surface, magnetic patches. So because of Coriolis force and other forces acting on the sun's surface, so these polarities migrate. One of these polarities migrates towards poles, and other polarities migrates towards the equator. And depending on their interaction, so every 11 years, this pattern switches. So because of that reason, the North Pole becomes south and the South Pole becomes north. Yeah, thank you.
Thank you, Krishna. So now we'll ask one question to Sajal, and this question is by Akash. What's the highest height of the prominence? So what's the highest height a prominence can go to? Sajal?
Hi, Akash. It's a good question. So as you already heard from this talk that prominence is a chromospheric structure. So these are the some plasma trapped with the magnetic field, which is hanging in the atmosphere, solar atmosphere. So you can see here in this picture that it could be like an arcade kind of shape, which is hanging from the solar surface. This is a chromospheric structure. So chromosphere extends around like a 10,000 kilometers from the photosphere. So the height of the prominence could be like a thousands of kilometer also. So far, like a 800,000 kilometer, it has been detected, which is stretched magnetic field to the outer layer of the photosphere. So it can be like a thousands of kilometer. So it depends on that structure.
Thank you, Sajal. So This is a nice question by Anirudh, and this question is to Shubham. So, how would the sun end its life cycle? Shubham?
Yeah. Hi, Anirudh. Nice question. So the sun is what we call currently what we call as a main sequence phase, which means that it's burning hydrogen in the core, and eventually it will run out of hydrogen in the core. And when that happens, the sun will move to the next stage in its evolution, which is known as the red giant phase, in which the sun will swell up quite a lot and engulf the inner planets, possibly even the Earth. And the sun, because it doesn't have enough mass to explode, so the sun is not going to have a supernova explosion. So the sun will end up, the core of the sun will end up as a carbon oxygen core, which are basically the ashes of the hydrogen and helium burning. And the carbon and the sun will not have enough mass and therefore not enough temperatures in the core to be able to burn the carbon and oxygen. So it will be left with an inert core of carbon and oxygen, which will be compressed to a very small volume, roughly the size of the Earth. And so this core is what we call as a white dwarf. So this will remain, and the outer layers of the sun will be ejected as a planetary nebula. So the core will be left behind as a white dwarf, and that will be the end stage of the sun's life.
So that was a nice question to conclude this talk. And as the sun dies, the sky becomes dark. But before that happens, and when we are still alive, let's go to the nighttime astronomy and explore the stars and the cosmos. Okay. Over to the nighttime astronomy session.
And see the cursor as well.
Raga, your screen isn't shared yet.
Okay, can you see it now?
Yes.
Yeah.
Yeah, sorry about that. So, yeah, welcome everyone to the nighttime astronomy session. Good morning. My name is Raga Deepika Pucha, and I'm going to be giving a brief overview of planets, stars, and galaxies, and then there will be follow-up sessions on cosmology and instrumentation. The main question to ask is, why do we study astronomy? So I'm sure many of you will agree with me when I say that curiosity is the essence of human existence, and that is where the study of astronomy comes in. So we want to know the answers to questions such as, how did the universe form? How do stars, planets, and galaxies form? How did our solar system come into being? Are there planets out there with life? And what is our fate in the universe? So astronomers all over the world are trying to answer some of these questions. But how do you attempt to answer these questions? And the solution for this comes from light. We use light from distant objects to study the universe. Specifically, the two facets of light are really important. One, light is an electromagnetic wave. Atre already mentioned that. And depending on its frequency and wavelength, it can be of different forms, ranging from low energy radio waves to high energy gamma rays. And based on the type of the radiation that we observe, we can learn more about the processes that happen in the universe. And another important fact about the light is that its speed of light is finite. This means that it takes light a fixed time to travel from one point to another. And this is really important since we can then use light as a time machine. For example, in this case, you can see the speed of light in real time. It takes light about 1.2 seconds to travel from moon to the earth. What this means is that when we observe the moon, we are not seeing it as it is in the present. We are actually looking at the moon as it was 1.2 seconds in the past. Similarly, light takes about 8 minutes to travel from the sun to the earth. So when we look at the sun, we are actually seeing it 8 minutes into the past. So this time machine part of light is very crucial in constructing how different objects formed in the universe. So before we venture out into space, let's talk about how small we are compared to the universe. So here we will be starting with our own Earth, and slowly we will be zooming out into the space. So please follow the cursor as I speak. So Earth here is like one among 8 planets in our solar system. And Sun is the closest star to us, and in comparison to other stars, it is just a normal size star. It is like a really small star. But even in this small star, we can fit about 10 lakh Earths inside this Sun. So you can imagine how big the Sun is. And the Sun and some of its neighboring stars are shown here, and you can barely separate the Sun from the other stars. The closest star system to us, as mentioned by Shubham earlier, is Proxima Alpha Centauri system, which is 4 light years away from us. A light year is a unit of distance in astronomy, and it is the distance light travels in 1 year, which is equal to approximately 9,000 billion kilometers. And these stars are part of our own Milky Way galaxy. And from this point, you cannot even see individual stars, like you cannot even separate the individual stars. There are more than 1 billion stars in our galaxy, and light takes about 1 lakh years to move from one end of the Milky Way to the other end. So in other words, diameter of the Milky Way is about 1 lakh light years. And when we zoom out even further from our Milky Way, we can see several galaxies, including our Milky Way and the nearest neighbor Andromeda, and some more galaxies. They form what is called as a local galactic group of galaxies. And several such groups form what is called as a supercluster of galaxies. And we are part of the Virgo supercluster. Finally, we see the observable universe, which is basically the universe that we can see with basically the equipment that we have. It's made of many such superclusters. Now let us think about this in reverse. So the universe is made up of about 10 power 11 galaxies. Each of them have about 10 power 11 stars. So in total, there are about 10 power 22 stars in the universe. So that is 1 followed by 22 zeros. So, and the sun is just one of them. So think about it, can you imagine the grandness of the universe? It's just personally for me, it's mind-blowing. So even though we are such an insignificant part of the universe, we as humans have the power to do something significant in this life that we are living. So this is just something to think about. So now let us start with exoplanets. Exoplanets are basically planetary systems outside the solar system. The primary question now is, why is detecting these other planets important? So this is important because it is the first step towards searching for life. It is also important because they might provide some clues about formation of planets and moons, and especially it can give clues about how our solar system came to be. So in the left plot, which is the latest plot, it shows the total number of exoplanets detected till now. And basically the color code shows the different detecting methods that are mentioned here. And you can see that we have observed about 4,000 exoplanets till now, and most of them, majority, were detected by the transit method. And this right side explains the transit method in a really simple way. So basically what we do is we measure the brightness of the star, and when a planet passes in front of the star, what happens is it blocks the part of the star, and because of that there's a dip in the measured brightness, and this amount of dip, we can use it to measure the radius of the planet. And if we take several measurements of this dip, we can also find how long it takes for the planet to make one complete revolution around its star. And this is all very exciting because there was an amazing discovery using this same transit method in 2017. A 7-planet system was found named the TRAPPIST-1 system, and this system was found to be much older than our own solar system.
So you can ask me why these planets are so amazing, considering we have already discovered 4,000 planets. So this is important because 3 of these 7 planets are in the habitable zone. So what this means is that based on the star the planets revolve around and the distance of the planet from the star, it is actually possible to have water on the surface of the planet. And if water is possible, then life may be possible. So here is an illustration of the 7 TRAPPIST planets compared to our own Earth. So you can see they are almost like similar to the size of the Earth, which is quite interesting. So I will now briefly talk about the life cycle of stars. So stars form from cold gas and dust nebulae, which are called stellar nurseries. They look something like this. So many stars form from this nebulae together. And based on the mass of the star, it follows different life cycles. So the first phase of all stars is the nuclear fusion of hydrogen into helium nuclei. In other words, protons fuse together to form alpha particles. And this phase is called as the main sequence phase. And after the hydrogen is exhausted in the core, hydrogen starts burning in a shell around the helium core. And this is called as the red giant phase, here as shown here, or in case of massive stars, it's called as a red supergiant phase. And after this phase, if it is a sun-like star or like a low mass star, it will slowly expand, shedding all of its outer gas layers. And this is called as a planetary nebula phase. It looks something like this. So when our own sun will reach this phase, it will expand so much that it will encompass even the orbit of the Earth eventually. So basically you can see that this small white thing in the middle, basically that is a central core, and that is left behind as a white dwarf. So our sun will also die as such a white dwarf in about 4.5 billion years. On the other hand, if it's a massive star, it will explode as a supernova, something like this, after the red supergiant phase, and either end up as a neutron star or as a black hole, depending on its mass. And galaxies are made up of thousands to billions of such stars. So the basic idea of the evolution of galaxies is that small galaxies form first, and then they merge together to form larger galaxies. So I'm going to play a simulation here. So you can see, so you can see here that, so here you can see different galaxies merging together. So each yellow point is typically a star in the galaxy. You can see the small galaxies are merging together to form bigger galaxies, or it might also happen that small galaxies get sucked up by bigger galaxies, and this is how the galaxy evolution takes place. And most of the galaxies have a supermassive black hole at its center. Even our own Milky Way galaxy has one, and it is called as the Sagittarius A star. In some galaxies, large amounts of dust and gas is being sucked onto these central black holes. And this results in a release of high amounts of energy. So such galaxies with an accreting supermassive black hole are called active galaxies. And this central region of the active galaxy here is called as an active galactic nucleus, or AGN for short. This region is very, very small. Its diameter is about like 3 light years. So I already told you earlier that the Milky Way has a diameter of about 10 lakh light years. So you can imagine like 3 light years in comparison to 10 lakh light years. So that's how small that region is. So even though these regions are that small, they actually produce more light than all the stars in the galaxy combined. So here I am showing you a comparison between normal galaxies and active galaxies. So you can see when you look at the normal galaxies, you can actually see the light from the stars, like here. But when you look at the active galaxies, these central objects, the light from the central objects is so bright that you cannot see anything else. So in fact, these active galaxies are actually some of the brightest objects in the universe, and they are often called as cosmic lighthouses. And as I mentioned in the beginning of the talk, different forms of light can be used to study different aspects of the universe, and studying the same object in different wavelengths can actually help us understand more about its formation and evolution. And that is what we call as multi-wavelength astronomy. So here I am showing a single galaxy in different wavelengths. So this first one is in UV wavelengths in UV, which is mostly used to study the young stars of the galaxy. And the second one is in optical regime, which is used to study the middle-aged stars, and it also helps us in learning about the mass of the galaxy. And this third one is in infrared wavelength, which gives us information about old stars in the galaxy. And this last one is actually in much larger wavelengths, longer wavelengths, and it helps us in understanding the distribution of dust in the galaxy. And astronomy has changed dramatically in the year 2015 when gravitational waves were discovered for the first time. I'm sure many of you were like hearing in the news about this. It was like an amazing new discovery. Basically, you can imagine space-time is like a trampoline, and when there is a disturbance, it is carried through space-time continuum as like gravitational waves, like waves. Basically, you can imagine them like waves in the water when you're like throwing a pebble in them. And astronomers built an instrument called as LIGO, which can measure these gravitational waves. And in September 2015, the LIGO collaboration found the first evidence of gravitational waves when two black holes merged together. Basically, two black holes combined together to form a bigger black hole. And basically, we can hear the frequency of these waves. So I'm going to play this video, and I want you to listen very carefully to the sound in the end. Astronomers called it as a chirp sound. So please listen to that very carefully. So that chirp sound is like very exciting. It's the sound when the two black holes finally merged, you know. So astronomers now have sound waves in addition to light waves. And this is amazing as it opens new windows into the universe, another way to study the universe, basically. Sorry. Yeah. So, and this window was again accessed when another gravitational wave event was discovered in discovered by LIGO in 2017. So this time it was a neutron star merger event, which was also accompanied by light waves. So immediately, as soon as we got the news about gravitational waves, all the telescopes were pointed in that direction, and we had images of the event in all the different wavelengths. So here I have just shown like UV and radio observations, but you can see this event happening here, like here, yeah. So this new era of combining electromagnetic waves and gravitational waves is what we call as multi-messenger astronomy. And we are currently living through a very exciting time of research right now, and it's going to be amazing. So thank you. I think Rebecca is going to continue on cosmology. So over to Rebecca.
Is the presentation visible?
Yes, looks good.
Just give me a minute.
Looks good.
Yeah, just give me a minute. Okay. Yeah. So thank you, Raga Deepika. So I am Rebecca. I'll be talking to you about cosmology. Now, so you guys have heard talks on starting with the sun, and then you moved on to galaxies, stars and galaxies, right? But where did all of this begin? Yeah, the origin and the fate of the universe has always been one of the big, among the major questions that still remain unanswered for the most part. Yeah, and this study of the origin and the evolution of the universe as a whole, here we deal with the universe as one entity, right? This study is termed as cosmology. Now, it turns out that in a very large scale, the universe appears the same throughout. So no matter in which direction you see, the universe looks the same. If you guys remember the slide that Deepika showed about the observational universe, you could see that the universe looked the same throughout. Yeah? So we say the universe is homogeneous and isotropic. So no matter from where you observe the universe, maybe from Earth or from a galaxy 100 miles away, it's going to still look the same. So, but has the universe always existed, right? Is it a finite universe or an infinite universe? Now, if it was infinite with infinite number of stars, no matter which direction you see, you will be met with a star. It's like, imagine you're stranded in the middle of a huge forest, right? No matter which direction you turn, you would look at a tree, you would see a tree. Yeah. So if this is the case, then the night sky should look as bright as it does during the daytime, right? But we don't see it. The night sky is dark. So why is the night sky dark? This question is attributed to the German astronomer Heinrich Olbers, after whom it gets its name, the Olbers paradox. The fact that the night sky is dark means that the universe is not infinite, but finite in space and time. Now, another major discovery that helped us understand the origin of the universe was made by Edwin Hubble in the 1920s. Now, what he used was something called as a Doppler effect, which I'm sure most of you will be familiar with. Imagine this. There is a cannon that fires 1 bullet per second, right? And you move the cannon towards a target. Now, as you move it towards a target, it would appear that it hits the target faster, right? Or the frequency is higher. And when you move it away, it would appear to hit the target slower or the frequency is lower. The same thing is applicable for any kind of wave. So as a source that generates wave moves towards or away from you, the frequency shifts to the lower or the higher frequency. It appears to shift, even though it doesn't. So when a star is moving away from you, okay, the light that you receive from it would appear to shift to the lower frequency end of the visible spectrum, which is red in color. So that's why we call it the redshift. And if it is moving towards you, it will move to the higher frequency end, and hence we call it blue shift. Now, Hubble found out that galaxies away are in fact redshifted, meaning they're moving away from us. And he not just found that, he also found that as you look at galaxies that are further away from us, the velocities are high, or the redshift is higher, meaning the velocity is high. So if you look at the graph over here, galaxies that are further away from us, the velocity is higher. So with these discoveries, Hubble was able to validate that the universe is expanding. Now, a finite and an expanding universe obviously will have a dark night sky. So we've established the fact that no matter where you see, the universe looks the same and everything is moving apart, right? Now, this would lead to the idea that at one particular time, at some point in the universe, all the galaxies come close together. Yeah, it's like the reverse process of the expansion. Yeah, so galaxies come close together and the universe started at a very hot, high density state. And this is what is termed as the Big Bang theory. This theory also predicted that there has to be some light left over from the initial expansion state that we should be able to see. And this light travels freely in space, but is stretched out. Like I said, it undergoes Doppler effect. I mean, it undergoes redshift. It redshifts until it is shifted to the microwave region of the electromagnetic spectrum. And this is what is called the cosmic microwave background radiation. And with its discovery, it serves as one of the major evidences for the Big Bang theory. So just like stars undergo different stages, or life undergoes different stages, human life undergoes different stages, the universe itself undergoes different stages in evolution. But what is it that causes these different stages in the evolution of the universe? Now, from the fact that the universe is expanding, the volume increases, thereby the density decreases, temperatures would decrease and the energies would decrease, right? And you would know that different processes require different energies. Yeah, atoms require different energies for formation, galaxies require a different energy for formation, and so on, right? So it is the expansion of the universe that causes the different stages in the universe. So universe started off with the Big Bang, where the density and the temperatures were so high. In fact, it was infinite, and the laws of physics breaks down here. And next stage is when it was around 10 power minus 36 seconds old, right? And this phase was called the inflation era, because this era witnessed a rapid expansion of the order of 10 power 26 times in a time of 10 power minus 32 seconds. That's like, imagine a strand of hair undergoing a rapid expansion and reaching the size of the Milky Way in that small fraction of a second. Now, this era introduced ripples in the smooth universe, right? Small discontinuities in the smooth universe, which served as a seeds for the formation of large structures. And when the universe was 1 second old, protons, neutrons, and electrons formed, and photons were interacting with matter. So light interacts with matter. And around 10 seconds and few minutes into the life of the universe, the first hydrogen nuclei formed, atom formed, sorry. And nuclei of light atoms formed. You have hydrogen, helium, and small amounts of lithium. And the next very significant stage of the universe was when the first neutral hydrogen atom formed. Now, this was when the universe was 380,000 years old. And at this epoch, light separated from matter, so no longer interacts with matter, and photons were free to move. And this is the light we see today as the cosmic microwave background radiation. Yeah, so this is the oldest light that we can detect. And after this, the universe went through what is called the dark phases, dark era, because even though photons were free to move, there were no light emitting sources as such. And the first light emitting source, or the first generation stars, formed only 100 billion years after the Big Bang. And from these stars, and from the formation of stars to the death of the stars, we have heavier elements being formed. And now we reach the present stage of the universe today, which the universe is around 13.8 billion years old. And the temperature has reduced drastically to minus 270 Celsius, and around 3 Kelvin. Yeah, so to give you an idea of, to give you a view of how the ripples in the cosmic microwave background cause structure formation, I'll play this video. So what you see here is the cosmic microwave. We reach the dark era. Tiny ripples, giving birth to stars, galaxies, clusters, superclusters. Finally, we reach how the universe looks today. And this is what we observe today. Now, from the fact that we've seen that the universe started at a very hot, high density state, right? If this is so, wouldn't the gravitational energy be so high that it would stop the expansion and actually, and everything around you contracts back to singularity? Yeah. Now, this would happen if the universe is made out of atoms and of matter and radiation that we are familiar with. But it turns out that we know about just 5% of the universe. Okay, 95% of the universe is still left unaccounted for. And this 95% comprises of two entities called dark matter and dark energy. Now, from an idea of gravity and Kepler's laws, and if you think about the solar system as such, planets that are further away from the sun move with less smaller orbital velocities, right? And than planets that are closer to the sun. Yeah, because the effect of gravity is less on planets that are away from the sun. But so we should expect the same for galaxies. But what we see here is the stars that are away from the center of the galaxy. So what is expected is as you move from the center of the galaxy, the velocity should go on decreasing, right? But what is observed is that the velocity does not decrease, but remains a constant. So you can see a flat curve there, meaning the velocity is almost a constant. So what is it that is keeping these stars in place? What is it that is causing these stars that giving the stars that extra push that they need? Yeah. So it turns out that these stars are held in place by matter that we are not able to see. Okay, this matter is invisible to us because it doesn't interact with light. And this is the so-called dark matter, which accounts for 22% of the energy density of the universe. And we've seen that the universe undergoes expansion, and recently it was found that the universe not just expands, but the expansion also is speeding up, it's accelerating. So that would mean that there is something pushing everything apart. Otherwise, your gravitational energy of galaxies should ultimately come into picture, stop the expansion, right? But this is not happening. So there is something that is pushing everything apart. So that something is dubbed as dark energy, which accounts for 73% of the energy density of the universe. Now it's called dark because the knowledge of it is still in the dark. So we know about the origin. We've got an idea about the origin of the universe. What about its end? Where are we heading? What is the fate of the universe? Now it turns out that there are three possibilities. One would in fact be that the universe goes on expanding until it stops and comes back, contracts back to singularity, and after which it can expand again. But this possibility can be ruled out because as of now we don't see deceleration, we don't see the expansion slowing down. The expansion is in fact speeding up. Okay, so we can remove the possibility of the big crunch. It is called the big crunch. Another possibility is the universe goes on expanding, okay, in a smooth rate until the temperatures fall down drastically and we all freeze to death. The third possibility is that it goes on expanding. The expansion accelerates so drastically that galaxies rip apart, galaxies move away with the speed of light. Your space-time continuum itself rips apart. So that's called the Big Rip. So which of these is the actual fate of the universe? Well, we still do not know. So what causes all of these facts that we've gathered? It's observations. Observations plays a very important role. Like I told you, and like Ragadeepika also mentioned, the fact that light acts as a time machine here. Okay, so the older the light gets, the further away into the galaxy, into the universe you observe, the further into the past you observe. And the cosmic microwave background radiation was one of the most significant observations which was detected by accident by Penzias and Wilson. The recent probe for this is the Planck satellite. We also have galaxy survey, like the Euclid satellites that probe the evolution of dark matter and structure formation. Yeah, so these satellites look at thousands of galaxies and how they are distributed in the universe. So as the universe expands, the distribution changes. And with these changes in the distribution, we will be able to find out or get an idea of dark matter and dark energy. So to give you a better, clear picture of the technology behind these observations, Arun will take over with instrumentation. Thank you.
Thank you, Rebecca. I'll try to share my screen now. I hope you can see the screen, and am I audible?
Yes, looks good. Sounds good.
Okay, so my name is Arun, and in the previous talks, you have learned a lot about the universe, about stars, galaxies, exoplanets. But how do we study them? For this, we use telescopes and instruments attached to them. And this is what I will be talking about. So we look at the universe at different wavelengths of light, and sometimes we call it colors. And depending on the wavelength of light we are looking, the type of telescope we use and where it is placed is also different. Atmosphere plays a big role in this because it absorbs light waves differently at different wavelengths. For example, X-rays and gamma rays and most of the ultraviolet rays are blocked by the atmosphere. So we use space telescopes to observe at these wavelengths. Visible light and some of the infrared light pass through the atmosphere and are observed by optical telescopes located at Earth. But preferably high, the more higher you are, the less atmosphere you have to deal with. For most of the radio waves, the atmosphere is transparent. So these radio telescopes, which are usually like large dish antennas or arrays of antennas, are placed on Earth. Now, observing at in different wavelengths reveal different details about the objects in the sky. For example, if you look at the Milky Way in visible wavelength, it looks a bit blotchy, right? And this is because of the gas and dust between the stars that block the visible light. But if you go to longer wavelengths, for example, in the infrared light, all of this light gets to cruise through and not be absorbed. So looking through the universe in different wavelengths reveal different things about the universe. Now let's talk about the telescopes. A telescope works by gathering light, and you could think of this as like a bucket in a rain. Like so, the telescope bucket collects light. The bigger the bucket, the more rain it collects. In case of telescope, this means collecting light from faint or dim objects in the sky. By using bigger telescopes, we are able to see galaxies that are very far away and which are very faint. So when we see galaxies which are very far away, we are looking literally into the past. And this has been explained before. So telescopes act like a time machine. A second use of the telescope is to see objects with greater detail. The bigger the telescope, the more closely separated details we are able to see. For example, in this image, like these are actually two stars which are close together, and the left image is from a telescope, a smaller telescope, and you can't separate out the two stars. But if you use a bigger telescopes, these two stars can be separated. So from all this, the one conclusion we reach is that we need bigger telescopes to gather more light, to look at objects that are further away, which are fainter, and to see smaller details of the object. The telescopes that you usually buy from shops or online usually looks like this, right? Like it had the left, you can see a refracting telescope. It has lenses, and on the right, you can see a reflecting type telescope, which usually uses mirrors. But an actual astronomical telescope that usually scientists use to study universe usually looks different and is often bigger. So let's try to look at how a modern observatory looks like. This is the Indian Astronomical Observatory located in Hanle. It's a small village near Leh in Ladakh, and it is one of the most active observatories in India right now. And as you can see, most from here that this observatory is located in a very high altitude. This is to reduce the effect of atmosphere when we are looking at the sky. Remote locations also uh, helps us to have very less light pollution, which are usually contamination from artificial lights. Contamination from artificial lights is one of the main reasons why we are unable to see a lot of stars in the night skies in cities. Most of the observatories also prefer like dry atmosphere to avoid light absorption from water vapor, etc. Now let's come to the telescope themselves. So inside this building is this telescope, right? Most of the optical telescopes looks like this. So instead of lenses, this what you see is a mirror, and this telescope is protected by a dome, and there are instruments attached to this telescope, and usually this blue box you're seeing is usually an instrument. And there are a lot of different kinds of instruments that are used in astronomy, and so two of the common ones are an imager and a spectrograph. So just to explain, a imager is, you can think of it as a camera. So it's mostly like a regular camera, but designed for astronomy. So they use sensors like this, which are like charge coupled devices. And the main use of them is to capture images with as much small amount of noise as possible. And you already have seen about things about spectrograph. So a spectrograph splits the light into different wavelengths. So in astronomy, sometimes we don't use prisms as it's mostly depicted. We use diffraction gratings, which give a better dispersion, and also it's more effective. So when we use diffraction gratings, we obtain an stellar spectra like this. So moving from here, how big are the current telescopes? We talked about telescopes a lot of times. How big are the current telescopes? It also depends on the type of telescopes. I'm showing like two of the optical telescopes here, the Keck telescopes in Hawaii and the GTC telescope in Spain. And they both are around 10-meter in size. And this is a big size for optical telescopes. And as you can see from here in the Keck telescopes, these are made up of hexagonal mirror segments. So these smaller mirror segments combine to form a large mirror. That's how bigger mirrors are formed. So this another one of these telescopes is a radio telescope, and it is in China. It's called the FAST telescope. And the whole telescope itself, the big dish, is itself built into a depression in a mountain valley, and the size of it is 500 meters, and this operates at radio wavelength. So but it's still pretty large. It's very difficult to imagine the size of this telescope. So we learned how big these telescopes are, but how awesome are these telescopes? And the answer is they are totally awesome. And I will show you some of the very great discoveries that has been made with these facilities in the recent times. And you have already heard about exoplanets, and and you also saw this figure, right, where when a planet moves across the in front of the star, you get a dip, and you detect that dip using an imager, which is an instrument we talked about. But you can also detect an exoplanet using a technique called radial velocity technique. So this uses spectrograph. So when a planet moves around the star, it causes the star to wobble a bit. And these wobbles get registered as small shifts in these lines in the spectra. And these the small shift of these lines can be used to detect these exoplanets. And while we are discussing exoplanets, this is another amazing result from one of the best instruments used, like currently used, which is like a coronagraph fitted in, used in Keck telescope. What we see here is the detection of planets around a star 100 light years from us. This technique involves blocking the central star light so that these faint planets around the star are visible. So it's amazing to see how far we have come in terms of technology and innovation, that we are currently at a stage that we are taking pictures of planetary systems of other stars. So this is another of one of the great images you may have seen in papers last year. It is the first recorded image of the black hole in the center of the M87 galaxy. This observation is very interesting because it was done using a lot of radio telescopes which were spread across the globe, and the observations from these telescopes were combined. They were synchronized using very precise atomic clocks, and they make these telescopes work like a single telescope of the size of the Earth. And it's very fascinating how the technology involved is imaging a black hole is. Now, if we are have amazing telescopes now, there is bigger and better telescopes and instruments coming up. So let's look at what this decade holds. So one of these exciting facilities is the James Webb Telescope. This is planned to be launched in 2021. So the size of this telescope is 6.5 meters, and it will be launched in this European Space Agency rocket, which is called the Ariane launch vehicle. And you may have already heard about the Hubble telescope, right? So Hubble telescope is 2.4 meters in diameter, and James Webb is 6.5 meters in diameter. This means James Webb compared to Hubble will give 2.5 times the resolution and 6 times the light gathering ability. And JWST will primarily observe in infrared wavelength. So one of the other exciting facilities that are coming up is the Vera Rubin Observatory that will start functioning in 2021. And it is named after an amazing scientist called Vera Rubin. And you have heard about dark matter in the previous talks. And she was a pioneer in the discovery of dark matter. And this is one of my favorite pictures of her, where she's looking into these pictures of galaxies in photographic plates through a microscope. And we have come a long way from photographic plates. We use sensors to digitally record the images of galaxies, right? And one of the cool things about this observatory, which has like 8.4-meter telescope, is that these cameras of this telescope have sensors which have 3000 megapixel camera. So it's like almost a gigapixel in size. So if your cameras in your phones are maybe of like 5 megapixels, these are like sometimes 600 times more number of pixels compared to what you have in your phone. So this telescope will scan the sky repeatedly at greater depth and with different filters. So these filters look at the sky as seen in this animation at different wavelength bands. So you can see how the filters are changed in this animation. It's also a decade where most of this extremely large telescope will come into action. So there are these 3 mega projects currently under development. The 30-meter telescope, which is of the size of 30 meters, as in the name, and the giant Magellan telescope, which is 24-meter mirror size, and the European extremely large telescopes, which is almost 40-meter in size. And they will gain almost 3 times as much in resolution to look at the more details, and also have 10 times more the light gathering power compared to the largest telescopes we currently have. And what does this all mean? Like, why do we need all these big telescopes, right? Like, we told about details. How does it look like in real? So this is the center of Andromeda galaxy when you take a picture with instruments in Hubble telescopes. And this is a simulation how it will look like when you take an image with 30-meter telescopes. You can individually resolve like thousands and thousands of stars in the center of the Andromeda galaxy if you use TMT. And this will provide a lot of scientific results in the coming decade. So I talked about these mega projects, and India plays a huge role in some of these mega projects. So one of the important projects I talked about is TMT, the 30-meter telescopes. India is contributing a lot in this project. So in segment polishing, you have already seen that these telescopes are made up of segments, right? It's made up, the bigger mirror is made up of smaller hexagonal segments. And this polishing of these segments, the support assemblies, which you see here, these are the support assemblies, and the edge sensors, some of them are made in India. And India is also contributing to building some of the instruments for these telescopes. India is also involved in the upcoming radio telescope called the Square Kilometer Array. So this is going to come up in the next decade also. And we are also involved in a gravitational wave observatory. This is very exciting. You heard the chirp from the gravitational waves, and India will currently involved in developing its own gravitational wave observatory. So apart from this, we are also building better astronomical facilities in India. This is one of the 3.6-meter telescope, which was very recently installed in Nainital. And this is one of the largest telescopes in Asia. And with this also, we are sending space satellites with telescopes. So AstroSat is one of the dedicated Indian astronomy mission sent to space in 2015. It can do observations in X-ray, optical, and UV ultraviolet spectral bands simultaneously. And following this, ISRO is planning a lot of space missions in the coming years. So the future is bright for astronomy. There are a lot of large projects and a lot of new technologies to be explored. What does this all mean? It means there are opportunities for everyone. If your interest is in optics, electronics, mechanical, software, astronomical instrumentation is an area which is very multidisciplinary and needs skills from all these fields. Sometimes you are parallelly working with on many of these technologies simultaneously. So this is where I will leave you at, that we need all of you and everybody is welcome, and we look forward to joining all these projects in the coming years. So from this point, I will stop, and you should, if you have questions, please type in the link in the description box. Please feel to ask the questions. So I will now leave it for the Q&A session.
Thank you, Arun. Viewers, I hope you people are enjoying our sessions. And now we are going to take questions on our session on stars, galaxies, cosmology, and instruments. So the first question is from Maitreyi, and Ragadipka is going to answer it. How is light year calculated, and who calculated this first? Ragadipika?
Yeah, thank you so much for this question, Maitri. So basically, light year, as I said, is a unit of distance, but unlike SI units like second and meter, they need not be generalized. So light year is basically a derived unit. What this means is it gets derived from other basic SI units. So light year is the distance light travels in 1 year. So you know that distance is equal to speed into time, right? So speed of light is a fixed quantity. So speed of light is 3 times 10 power 8 meter per second. So that's in SI units, meter per second. And then time in 1 year. So you convert the year into seconds. So that is 365 days into 24 hours into basically 3,600 seconds. So you multiply that and you get the final distance, which will be in meters. So that is how the light year is calculated. I hope that answers your question.
Thank you, Ragadipika. We are going to take the next question, which is for Avinash, and it's from Tejas. The question is, can the transit system or variable brightness be used to measure distances? Avinash?
Thank you, Sam. It's a very nice question, Tejas. So this is how most of the exoplanets are detected using the transit method. So if you have a star here and if you have a planet moving around it, if we look at the star, we won't be able to see the planet, but the planet will be blocking the light of the star, a small light of the star, for a short period of time. So what we look at is what is the period at which the planet is revolving around the star. So once we know that, using Kepler's laws, which you very well know of, which you have learned in schools, once you understand what is the periodicity of the orbit, so let's say every 10 days it's orbiting the star, every 15 days it's orbiting the star. So you can find out from Kepler's laws what is the radius of the orbit very clearly from that. So I hope I answered that question.
Thank you, Arun. We'll take the next question, which is, could you explain more about the main sequence with respect to the Hertzsprung-Russell diagram? So I'm going to answer this question, and like to share my. I'm sharing my screen. just to make it convenient for you to understand it. So I hope the plot is on everyone's screen.
Yep.
Now, Ragadipika showed you this beautiful cartoon which showed you the evolution of stars and how stars of different masses will evolve. The low mass stars will generally finish up their hydrogen and then end up to become a white dwarf, and the higher mass stars, which are a few 10 of solar masses, they might end up in being a black hole or a neutron star. Now, if you look at the sky and you just sample a group of stars and measure their luminosities or the brightness, and you calculate their temperature, and you just plot their luminosities or brightness, the amount of energy that they're radiating versus the temperature of the star, that gives rise to what we call as the Hertzsprung-Russell diagram, or luminosity versus temperature diagram. And when you do it for a group of stars, you will see that most of the stars, they will lie on this line, which is called the main sequence. And what is the main sequence? It is the phase of the star where hydrogen inside its core is being converted to helium. Okay, and this is the phase where the star spends most of its lifetime. So that's why when you take a snapshot, you'll find most of the stars in this particular phase across the main sequence. So the sun is, somewhere over here, as you can see, and then there can be stars which are more massive than the sun, which means that they have more hydrogen. Now the question which rises is, why are they taking, if you see the lifetime, why are they spending less time? The massive stars are spending less time in the main sequence, like less than a billion years, uh, even if they have so much of hydrogen. Another point, crucial point, is if they have huge mass or this huge reservoir of hydrogen, the temperature inside the core of the star, or the inside, the core of the star is has very high temperature, and it will act like a more faster engine in converting hydrogen to helium, and that's why it will take less time to evolve off the main sequence as compared to a sun-like star. So this is so to summarize, basically main sequence in the HR diagram is the phase where every star spends most of its lifetime, which can depend on the mass of the star. It can be from a billion years for a sun-like star to a million years for stars which are 5 to 10 times more massive than the sun. So we are going to take another question, which is related to this. And this is for Arun. The question is from Tejas, again, which is, does a supernova give rise to both a neutron star as well as a black hole, or any one of them? And at what stage in life would the sun explode in the form of a supernova? Arun?
Thank you, Sam. Hi, Tejas. I hope most of these points were raised in the talk itself. As you would have heard, the sun is not massive enough to go supernova. So sun will not end up as a supernova. And as far as your other question is concerned, when a supernova does occur, the remnant, that is the object that is left behind after the supernova, depending on its mass, will either end up as a neutron star or it will end up as a black hole, not both the entities together. Thank you.
Okay, since we are talking about stellar evolution, there is another question for Shubham, and this question is by Melvin, who asks, what is a neutron star? Shubham?
Yeah, excellent question. So you have already heard that stars that are massive, roughly at least 8 to 10 times the mass of the sun, will explode. Their cores will collapse, and that will lead to an explosion, which we call as a core collapse supernova explosion. And the core that is left behind can be a neutron star, and this is an extremely dense, compact object, which is mostly made up of neutrons. So the protons and electrons come together, get squished due to the high densities, and become neutrons. And the densities can be extremely large. In fact, imagine a sun-like mass concentrated into something as small as a city. So the densities can be extremely large, and roughly a spoonful of material from a neutron star would weigh roughly as much as a mountain would weigh on the Earth. So, and some of these neutron stars could be spinning at a rapid rate, and these are what we call as pulsars. Thanks.
Thank you, Shubham. I'll take a couple of more questions on planets. So this question is for Preeti from Asher John. And the question is, why does our solar system have so many planets while most stars have maybe 1 or 2 stars?
Hi, Asher. So that's a great question. So I believe the question is why other stars have only 1 or 2 planets. So considering that's a question, let me go along. So here's the thing. So the first time an exoplanet was even, I wouldn't say discovered, but the possibility of the existence of an exoplanet was sometime in the 1970s. They chanced upon this data that told them that maybe it exists, but it was not conclusive. The first conclusive evidence of an exoplanet came in 1995. And since then, up to now, if you remember the image that Ragadipika had shown, we have over 4,500 exoplanets that we have discovered in the last 25 years. Now, did these exoplanets not exist before, or what happened over there? It's just that they always existed. But we were not looking for them, or we were not observing them, and we didn't find them. So the first time we came across an exoplanet, we started having dedicated missions. We started having dedicated instruments explicitly to look for exoplanets. And since then, we are only finding more and more and more of it. So this is called an observational bias, basically. So where what your question you're asking, why we're only seeing maybe 1 or 2 planets around other stars, is something similar. So what happens in that case is we are finding planets which are easy to find based on the techniques we are currently employing. It's not that the other stars don't have more planets around them. We are only finding those that can be easily found with the techniques we have. So for example, let's say that we were on a completely different star and looking at our own solar system. Chances are we will initially discover only Jupiter and Saturn because they are the biggest planets around our sun. And our newspaper from that star will read, we have discovered 2 planets around this other star. And it would have taken us few more months and few more years by the time we discovered, say, Mercury and Neptune and Uranus, etc. So it's not that these planets, more planets don't exist around a star, but given our capability of what we can observe, especially with exoplanets, which are hard to observe, we are preferentially observing the ones that are easy to observe, like the big planets. So one example is the TRAPPIST system, for example, that Ragadipika showed. That is a system of 7 planets. So the more we observe, the more we are going to find. It's not going to be limited to just 1 star and 1 or 2 planets around them. I hope that answers your question. Thank you.
Thank you, Preeti. A couple of questions from Cosmology section, and one is for Arun. So this is by Asher John, and Asher asks, matter has mass which causes gravity. So is dark energy caused from antimatter, which is antimass?
Yeah, thank you, Sam. Now, good question. Now, the short answer is no, because here what we are talking about is the dark energy is something responsible for accelerating the expansion of the universe. That means it's pushing all the galaxies and, okay, in your words, pushing all the mass away from each other. Now, antimatter behaves the same way gravitationally as matter. So it does not give you negative gravity as such. So as far as we are concerned now, as far as we know now, we don't know the exact nature of dark energy. What we do know is Since mass, your regular matter, including even dark matter, creates something called as positive pressure. Your dark energy creates a negative pressure, causing it to accelerate the galaxies farther apart. Now, there are different models as to what dark energy could be. I think this also will answer another question here. One such most popular model is that cosmological constant could be a possible model of dark energy. So this is the most popular model that we have today. Thank you.
You're muted, Sam.
Yeah, sorry about that. So this question is an instrumentation question from Ananta Karana. This is for Arun Surya. The question is, which is the best telescope for beginners?
Hi, thank you for the question. So if you're a beginner, maybe like you don't even need to get a telescope. You can start with a binocular, like a good pair of binocular, like binoculars is pretty good to see most of the night objects like Jupiter or uh, Saturn. And if you get your hands in for like a 4-inch small telescope, it's even better. But like if you go for large telescopes larger than 4-inch and like the field of view is small, you will need tracking, and that starts getting into expensive territory. So for a beginner, I would suggest get a good pair of binoculars, and that's just pretty good enough to see most of the objects. Okay, yeah.
Thank you, Arun. So please keep your questions coming. We will be moving on to the next session, which is on career. So don't get worried, don't get upset if your question is not answered in this session. In our last session after the career, we are going to come back and answer your questions. So please keep filling up the form and keep asking questions. So now we are going to move to the career section.
Samoda, am I audible?
Yes.
Okay.
Yes, Sajal. Yeah. Over to you.
Hi, everybody. I welcome you to the last presentation of today's session about career in astronomy. I hope you have a lot of fun about astronomy. You got to know a lot of research, interesting research area in astronomy, starting from daytime to nighttime astronomy and instrumentation. So I hope you are not saturated with that lot of information together. So having your interest in astronomy, you can pursue your professional career in astronomy, or you can keep it as your hobby. So here I'll talk about how you can pursue as a professional career or hobby in astronomy. So let's start. So when we talk about that professional astronomer or researcher in astronomy, so what researcher do in astronomy? So they can study different objects in different way. So one thing they do, that they do theory or simulation or modeling. So knowing the physics, so they develop mathematical models to understand the various physical processes occurring in the universe. So in this way you can study different objects. Or there are a lot of existing big telescopes are there with which you can observe different objects, and with this data you can analyze them and find out the interesting thing. So this is the observation and data analysis section. Or you can be part of in the development of different instrumentation like telescope, spectrograph, imager, so different things. So in to have a career, professionally career in astronomy, you can choose any of the subject or combination of any of them. So how do you choose your career path in India to do research in astronomy? So you all are student, so school students. So in +2 or 12th standard, you can take like a science subject, physics, chemistry, mathematics, as you take the science subject. After that, you have two way to get into the research in astronomy. One of the way is take a basic science path, like Bachelor of Science, where major subject will be in physics and side subject will be mathematics. After bachelor, you can go for masters in physics or applied mathematics. So these things you can do different universities or either in India. After completion of your masters, you can get into directly PhD in astronomy or astrophysics. So before that, you have to qualify some national level exam test like JEST, GATE, or NET, or different institute where you would like to study. You can check their websites. They may have different individual exam for that also. So this is one of the way studying the basics sciences, physics and mathematics, and you can get into PhD in astronomy and astrophysics. But there are another way. Suppose you are interested in the engineering field, so you can take after your +2 Bachelor of Engineering, so where you can take like a computer science or electronics or electrical or instrumentation or optics related subject. After bachelor, you can qualify national level test like a GATE. Then you can get in the MTech, where you can study astronomical instrumentation or optics related subject. After that, again in the similar way, you can get into PhD in astronomy and astrophysics. So this is the engineering subject. But there are some institute in India, after Bachelor of your Engineering, after qualification, after qualifying the GATE, you can directly get into PhD in astronomy and astrophysics. So this criteria, you have to see individual institute websites. They may prefer just GATE, NET after your master or BTech, or do they may have also their individual exam. So any of that entrance test you can qualify and appear for the interview and finally get into the PhD in astronomy and astrophysics. So after doing your PhD in astronomy and astrophysics, you can still continue your research, and finally you can be a scientist or assistant professor in a research institute or any reputed university. So suppose you are interested to study or do research in abroad, how do you go for that? So the two main hotspots like a study in astronomy and astrophysics is Europe, Australia, or USA. So for Europe, your path will be like you can do Bachelor of Science in major in physics. After that, you can appear for the exam like a IELTS, which is proficiency in English. So this is required for UK and some other some few European universities, not for every countries. So you can appear for exam, then you make a score, then you can go that particular country for the Master of Science, again major in physics. Then after that, you can go after your masters, you can go PhD in astronomy and astrophysics. But you suppose you want to study bachelor and masters in India, after that you want to go do PhD in astronomy and astrophysics in the abroad, Europe or Australia. So again you have to qualify that IELTS. Then you can choose your university where you want to study. For USA, so this is a similar way, but after your basic degree in bachelor like engineering or sciences, so you have to qualify GRE and TOEFL, which is required. After that, you can join some university where you can do masters, and after masters in the similar way you can get into the PhD. So as I told, for Europe and Australia, suppose you want to do masters in India, then after that you want to go for PhD in abroad. So you can qualify after your master GRE and TOEFL, then you can go directly PhD in astronomy and astrophysics in USA. So these are the exam is more important to go to the different countries. So at the final, when you continue your research in astronomy, so you can do postdocs or something like a more research experience in different institute. After that, you can join as a scientist and professor in that in India as well as in different country, the research institute or universities. Here I can show you some of the university in India which offers master's program in astrophysics, like Delhi University, Pune University, IIST Trivandrum, then Anna University in Chennai, Andhra University, Osmania University, the St. Xavier's College or University in Kolkata, IIT Indore. So these are the places where you can directly join for astrophysics in master's program. So after your masters, so you may not be like a directly sure that you want to continue for PhD, I mean research. So before getting to the jumping to the big research, you can always have a preliminary flavor and research methodology. How do you do that? Like you can attend some summer or winter school conducted by astronomy research institute like Indian Institute of Astrophysics, IUCA, or you can apply for an internship for 3 to 6 months during your bachelor or masters in IIA or IUCA or PRL. And another way is that you can apply to do bachelor's or master projects, like a 3 months, 6 months projects in this astronomy institute. So these are the way you can see that how research is going on, or you can have a preliminary favor. Or another thing also you can do, you can attend some outreach program organized by those Indian institute and interact with those students who are organizing this kind of event or faculty member. So then you will have a better idea that how and which subject they are doing research and which institute is more favorable for you to your likable subject. So these are the major institute in India where you can do directly PhD, like a research in astrophysics, then PRL Ahmedabad, TIFR in Mumbai, IUCA Pune, NCRA Pune, then ERIS Nainital, IISc Bangalore, IIA Bangalore, RRI Bangalore. So these are the professional research institute in India where directly you can work in the observatory itself. So there are, apart from this observatory and research institute, there are some university and ISAR in India where you can directly get into the PhD program. Like ISAR Mohali, ISAR Bhopal, IIT Bombay, ISAR Pune, IIST Trivandrum, then Banaras Hindu University, SN Bost, ICSP, ISAR Kolkata, NISAR Bhubaneswar, Osmania University, ICTS Bangalore, then ISRO Satellite Center in Bangalore. So here, after your bachelor or master's, you can directly go and join as a PhD scholar. So for that, you have to qualify GATE, NET, GIST, or individual institute exam to get into this kind of institute for your PhD program. So suppose you are not sure that you will continue directly to the research, but after bachelor or master research, you want to get into as a professional job in this institute like a ISRO or IUCA. How do you do that? You can always take this job. You can be like a telescope support or observatory support, lab assistant, or you can be the part of the development program like engineering subjects. So directly your bachelor, after your bachelor and masters, you can join to the ISRO, Indian Institute of Astrophysics, IUCA, this kind of institute. After your bachelor or masters, you can also directly go to Europe or USA for your job. So there are some industries that build instrument, especially for space agencies like ESA and NASA. We already know these things. So after your bachelor, you can directly apply. So if it is matches your subject, then you can always go for this. And another thing you can do, you can take up some research-based job in industry, which manufacture like a telescope optics, mechanical, electronics components, or camera. So these are also like after your bachelor or masters, you can join. So you don't need to go directly research, but you can also always can do the technical job in company or industries. So, but if you are not sure that you will make astronomy as a professional career, you can always keep it as your hobby. So for that, what you have to do, you can visit planetarium and attend the Skywatch Association, like a Skywatch session organized by so many planetarium. So there are 47 permanent planetarium in India that have public astronomy and space viewing programs. So here I have listed some of them. You can go through that. So depending on which city you're living, you can go close by planetarium and you can keep as your hobby alive. Or you can join like an astronomy club or interact with the amateur astronomer. The Bangalore, there is a ABBA, Association of Bangalore Amateur Astronomer. Or you can also go to the Jyotirvidya Pori Sanstha in Pune or Jantar Mantar Jaipur and Delhi. So these are the join astronomy club and interact with the amateur astronomer. You can also take part in national and international astronomy Olympiads. So there are some there are some small projects also you can do in that astronomy as your hobby. So for that, you have to check this link, zooniverse.org. And suppose you want to do some small course, like a certificate course, that is also possible. You can go to Planetarium in Bangalore, there is a REAP course, or there is also a 100 hours certificate course in astronomy, which is in MP Birla Institute for Fundamental Research. So this is the way you can do your hobby also. So here I have listed, as I told, that after bachelor or masters, you can do a job or a internship program in ISRO, IUCAA, IIA, it is a different institute. So here are some links, you can go through that. So every 6 months or every 1 year, they can post that we are looking for this such candidate. So you can also apply according to your interest or your background. And for opportunity in Europe and USA and Australia and China also. So you can go through these links. So this link will send you through email. So thank you for attending this session. And if you have any question for particular career path direction, you can write here, career related question, and submit it. Then we will try to answer you. Thank you.
Thank you, Sajal, for this wonderful talk. And viewers, I hope you're there with us and you found Sajal's presentation. I hope you found it to be useful in planning for what you're going to do in future. So now what we are going to do is we are going back to the questions that we have not answered yet. So we will do it session wise. So first we will take the daytime session questions, and then we will move to stars, galaxies, and then finally career. And we are already receiving a lot of questions. So thank you for sending in your questions, and keep them coming. So now we have moved to the daytime session. So the first question is from Tejas for Soumya. And the question is, what elements cause presence of spectral lines in the light spectrum or electromagnetic spectrum of the sun?
Yeah. Thank you for that question, Tejas. Yeah, so what spectral lines we see basically depends on what the chemical composition of the sun is, and basically what elements are present on the sun and how abundant they are. So what we know is sun is made of about 74% of hydrogen and 25% of helium, and remaining 1% consists of other elements like carbon, nitrogen, oxygen, iron, and so on. So, for example, in the solar atmosphere, we see transitions, the spectral lines which occur because of the transitions in elements like iron, sodium, carbon, calcium. So I hope that answers your question.
Thank you, Soumya. Going on to the next question, which is from Ananya, and this is for Mohan. Can the solar flares emitted by the sun be used to power the earth? Mohan?
Nice question, Ananya. So solar flares are mostly in the high energy, the UV or the X-ray regime. So they cannot be seen on the surface of the Earth because the atmosphere already blocks it. So if you really want to see those X-rays, you will have to send satellites to space. That's why there are solar observatories in space to view the solar flares and stuff. And the energy due to solar flare, meaning the X-rays or the UV radiation, or like the entire electromagnetic spectra that you get from the flares, it's too little and it's sporadic. So you cannot use it as a continuous source of energy. Rather, you can use the sun's black body spectrum as your energy source, because it's much more consistent and you have much more efficient. I mean, research has gone in and like you have very good photovoltaic cells like which converts that light into electricity. So no, flares cannot be used for energy production. I hope I answered your question.
Thank you, Mohan. Now, the next question is for Avinash, and it's coming from Pratham, who is asking, harvesting energy from sun via solar panel is very inefficient. What are the possible ways for efficient energy harvesting techniques that we may see or happen in future?
Hi, Pratham.
Avinash.
Yeah, so that's a very nice question. So as you said correctly, solar panels are inefficient in converting the sun's radiation into electricity. Commercial solar panels have about 17% efficiency, but we have solar panels on satellites, which are much more efficient, about 30 to 40% efficient in converting solar energy into electricity, but it's very expensive. The reason for the inefficiency of the solar panels is that the sun's radiation is a very dilute form of energy. What we are taking is there is a fusion reactor which is millions of kilometers away, and we are just looking at it from far away, and we are trying to collect the radiation coming from that. So, as you rightly said, one of the research areas which is happening in power engineering, not in astronomy, is the field of nuclear fusion, which is trying to replicate the sun, a small part of the sun on the Earth itself, using hydrogen, combining hydrogen to create deuterium and heavier elements and generate energy out of it. But one of the challenges that we find is to contain the plasma. You have seen in the daytime astronomy presentations the kind of high energy plasma which is created on the sun's surface. So if we find, one of the biggest challenges, if we find a way to contain the plasma in fusion reactions, if we are able to contain that amount of energy, either using a magnetic field or using lasers, which are areas of research happening all around the world, then that sounds like the best possible avenue for limitless energy. Who knows? Yeah, so I hope I answered your question.
Thank you, Avinash. The next question comes from Gaurav, and this question is for Krishna. And the question is, can the magnetic field on sun increase beyond its limit? And if it increases, what will happen?
Hi, Gaurav. That's a nice question. So the typical magnetic field, what we call the bipolar field, regularly gets amplified because of the differential rotation and convective motions. And it gets converted between poloidal and toroidal field between each other because of the Coriolis force, differential rotation, etc. So what you said is correct, and I don't think there is any such limit as such in the amplification of the magnetic field. Occasionally, we do see very large sunspots with high field strengths. So if it reaches very high limit, what will happen? We will see massive flares maybe, and then because of that, it can cause harmful effects on Earth. That is correct. But rather than having said that, rather than the strength of the field, it is also the vicinity of the ambient other active region fields that will cause these harmful effects. So that's all I have. I answered your question. Thanks.
Thank you, Krishna. Can you stay with us to take this next question?
Sure.
This question is from Gautam Krishna, and Gautam asks, why can't we find the corona, or why has the corona greater temperature as compared to the photosphere and the chromosphere?
Hi Gautam, good question. So I think, or how do we find, maybe your question is perhaps, I would rephrase the question as, how do we find the corona has greater temperature compared to the photosphere and chromosphere? So indeed, the corona is about 200 times hotter. It's a million Kelvin plasma on an average compared to the photosphere and chromosphere, which are few thousands. And in chromosphere, it is tens of thousands of Kelvin. So how did we find the corona is hotter? It goes back to 1930s and 40s when when the corona was being mostly observed by eclipse observations. So there we found strange spectral lines which were not explained by any of the elements that were known by then. And then later it was found out that those elements are caused by highly ionized elements such as highly ionized iron. So like 13 times ionized iron or 14 times ionized iron. So those emissions were coming from those emission lines were coming from those highly ionized iron. So these highly ionized iron elements can only exist in the atmosphere at very such high temperatures of like a million Kelvin plasma. So that's how we found out that corona is so hot. Yeah, thank you.
Thank you, Krishna. Now I'll take another question, which is somewhere between solar astronomy and related to career as well. And this question is from Maitri, and this is for Varun. And Maitri needs some more information about the Kodaikanal Solar Observatory. So Varun, if you can speak a little more about it.
Yeah. Thank you, Sam. Hi, Maitri. So I don't know if you are interested in history of Kodaikanal Observatory, which I am sure you are not. So I'll focus on the past and current contributions from the observatory, which was first established as a Madras Observatory in 1890s and currently owned and operated by Indian Institute of Astrophysics. This observatory is on southern tip of Palni Hills, 4 kilometers from Kodaikanal city in Tamil Nadu. The first ever discovery from this observatory was the Evershed effect in January 1909, named after John Evershed, who was director, in fact, the first director of that observatory. This Evershed effect is related with the radial flow of gas across the photospheric surface of the sunspot. The gas flows from umbra, that inner border, towards penumbra, that outer edge. You may, if you are interested, you may read about this on the internet. Then the other work or other observations is what is happening is the hourly observation of the surface temperature, pressure and rainfall are made here and transmitted to Indian Meteorological Department and World Meteorological Organizations as well for use in weather forecasting and other research purposes. Apart from this, in one of our in the talk, in solar talk, we had said also about this solar data. So 100-year solar data is available right now, and it is digitized for everyone basically. So you can use this for your research purposes. Apart from this, there are public outreach events also happen here, including tours of the facility, access to the astronomy library, nighttime telescopic sky viewing, presentations on the special university level courses, seminar, workshops, and etc. etc. So these are the few, like what do you call, the contributions right now happening with this particular observatory, Kodaikanal Observatory. I hope I have answered your question. Thank you.
Thank you, Varun. We will now move to some questions from Stars, Galaxies, Cosmology, and Instrumentation session. Now, the first question is from Asher John for Ragadipika, and I'll combine this with another question from Gautam. So the question is, how far are we from the point where the Big Bang occurred? And the next question is, how vast is our observable universe? Raga?
Yes, thank you so much for these questions. So the answer to the first question, it's a really good question. How far are we from the point where the Big Bang occurred? So you would be like it's a mind-blowing thing to know that the theory, basically what we say is space-time did not exist before the Big Bang. So what that means is when Big Bang started, that's when space and time started. So there is no such thing as space and time before the Big Bang. And we have evidence now that universe is expanding. So what this means is that in a normal sense, in an intuitive sense, if we think about it, it means that basically all the galaxies are moving away from one another. But another way, like to think about it, is basically more space is being created between the galaxies. So if you think in this way, then there is no such thing as a point in space where the Big Bang actually occurred. So we cannot actually physically say the distance between the point where the Big Bang occurred and where we are related. So that's not actually physical. And the next question, which Gautam asked, how vast is our observable universe? So that is based on the current cosmological calculations that we have. So the diameter of the observable universe is about 93 billion light years. So yeah, thank you.
Thank you, Ragadipika. I'll move on to another question, which is sort of related to this, and this is for Shubham by Anirudh. And the question is, what is the value of Hubble constant and how was it discovered?
Yeah, thanks for the question. So as you have heard, we know that, so it was Hubble who first noticed that the galaxies are moving away. So all the distant galaxies are moving away from us. And this we learned by measuring the redshift. But it's not just that the distant galaxies are moving further. The farther they are, the faster they're moving away from us. And this is what is called as the Hubble's law. And so if you plot a diagram with velocity on the y-axis and distance on the x-axis, you get a straight line. And the slope of this straight line is what we call as the Hubble constant. And so this can be measured in principle. If you have the velocity from the redshift and the distance, you can measure the Hubble constant. But in practice, it's much more difficult to measure precise distances to far away objects. So estimating the Hubble constant is a challenge. And there are multiple ways to do it. You can do it using supernova observations. You can also do it using cosmic microwave background observations. And with the advent of gravitational wave astronomy now, we have a third method to estimate the Hubble's constant. Thanks.
Thank you, Shubham. Now, moving to another question, which is from Surya. And this question is for Mohan. And Mohan, Surya is worried. He asks, when does the moon die? Can you please answer him?
Yeah. That's a nice question, Surya. So this answer is based on some simulations that's been performed. So you know that as the moon is revolving around the earth, it causes tides, right? So the earth is rotating faster than the revolution of the moon. So what happens is when the earth is rotating, it drags the moon along with it because moon is tidally locked to earth. And this dragging makes the moon go a little further away every year. It's like around 1 inch per year or 1.5 inch per year. So if we continue to evolve this with time, we'll see like in 50 billion years or so, the moon will reach a stable orbit where it is no longer tugged by the Earth's rotation. But like Shubham and others were pointing out, our sun is going to become a planetary nebula and die as a white dwarf. But in the process of becoming a planetary nebula, it is suspected that it will engulf the Earth and in the process the moon as well. So the Earth and moon might face the same end where they'll be engulfed by the sun. This is one of the theories. This is how the moon might die. It will die just like the Earth.
Thank you, Mohan. We will take an instrumentation question now. The question is by Akash Vishwanath, and this question is for Arun Surya. Now, Akash asks, are refractive telescopes better than reflective ones? And what is the optimum length for both?
Uh, Thank you, Akash, for the question. So, usually refracting telescopes are not as much better than reflecting telescopes. Reflecting telescopes are much better. Two reasons come to my mind. One is that refracting telescopes, which uses lenses, usually have something called chromatic aberration, which is the light, the red light, the different colors in the light, right? The red, blue, or different wavelengths focus at different points, or like the where they focus changes depending on the wavelength of light. So this creates a blurring effect. So that is one reason. Other is that for bigger telescopes, like the lenses, the refracting telescope consists of lenses, and they have to be supported by on the rim, right? So for big telescopes, if you construct even able to construct big lenses, they have, it's very difficult to build structures that can hold them. uh, but for mirrors it's much more easier. And regarding the length of the telescope, so I guess it comes down to the focal length. So for smaller telescope, the length of the telescope comes down to the focal length of the objective, and this is dependent on magnification. So depending on your magnification, like how much like magnification you obtain, the length of the telescope changes, and there is no optimal. So it depends on how much field of view you want to see, whether you want to see a wider field of view or small. So that's all. Thank you for your question.
Thank you, Arun. I'll take a couple of more questions from the stars and galaxies and cosmology section and instrumentation as well. So this question is for Arun Kenath, by Anirudh. And Anirudh asks, what astronomical objects would be the last remaining remnants of the universe? Arun?
Thank you, Sam. Good question, Anirudh. I'm sure you heard about the eventual deaths possibilities of how the universe is gonna end, right? So one possibility is the galaxies will stop expanding and then collapse and give you the big crunch. So everything will end with that. Or another possibility is the expansion will continue forever. If the dark energy remains constant, the expansion will still continue, and the universe will end up with something called as a eventual heat death of the universe. The other possibility is if the dark energy is in fact increasing with time, that is the most interesting possible fate for the universe, at least I think so. The expansion will keep on accelerating. Eventually, all the galaxies will be ripped apart, all the structures, including stars, will be ripped apart. Eventually, even atoms and space and time itself will be ripped apart. So that scenario is called as a big rip scenario. So these are the possible eventualities for the objects that we see in the universe: big crunch, or eventual heat death, or a big rip. Thank you.
Thank you, Arun. moving to another question about telescopes. And this question is from Surya MV. The question is for Avinash, and Surya wants to know which is the largest telescope in the world and how can it be used? Avinash, over to you.
Thank you, Sam. That's a good question. So the largest telescope in the world with a single mirror, the largest optical telescope in the world using a single mirror is the Gran Telescope Canaria, and it is in Spain. And the largest radio telescope in the world is, as Arun showed, the 500-meter diameter fast radio telescope in China. So the next part of the question is more interesting. How can it be used? So regarding the use of all telescopes among the astronomy community, what we usually do is, because there are, as you have seen now, there are more interesting questions to ask than there are telescopes around the world. We have to choose, unfortunately, what all questions to ask with the telescopes that we have. So we astronomers, we write proposals saying, okay, these are the questions to ask, and why are these questions important for humanity's understanding? And we decide among ourselves how good the question is on several cases of merit, and we decide accordingly whether a telescope can be used to measure or answer these questions. And this is especially important because telescopes and instruments are very expensive, and every night of observation with telescopes, especially with the largest telescopes, can amount to hundreds of thousands of dollars or rupees, whatever your currency is. So it's actually very important for astronomers to ask the right questions and put it in a way so that humanity can get the maximum output out of it. I hope that answered your question.
Thank you, Avinash. Now, moving on to another question from stars and galaxies. Now, Akash Vishwanath wants to know from Ragadipika that are quasars also active galaxies? However, they are several billion light years away. So, are they still present?
So, Akash, that's a really good question. So, yes, quasars are also active galaxies. In fact, basically, the term quasar means a quasi-stellar object. So, astronomers are basically very bad at naming things. So, when these quasars were first discovered, they look like stars because they are really far away, and they are usually unusually bright. So, we didn't actually know at that time that they were actually galaxies with an accreting supermassive black hole. So they were thought of as quasi-stellar objects because they definitely know that they are not stars. And so yeah, quasars are actually active galaxies, and they are located really far away. The oldest quasar that we found till now is about it's actually when the age of the universe was about 700 mega years, million years. So that's the thing. And the other thing is that we do not know how the objects that we observe far into the future are actually now. So we can only see into the past. We don't know what happened to them and what they are, which state they are in now. But I think they one of the things that we can assume is probably that since they are galaxies, they merge together to form bigger galaxies, and they are part of some galaxy like Milky Way right about now. So I hope that answers your question.
Thank you, Ragadipika. Can I request you to stay with us and answer another question from Akash, which is interesting. And Akash asks, has the existence of dark energy been proven?
Yes, that is another very important question. So So the dark energy and dark matter are like theoretical constructs that we have to explain what we are seeing. So we cannot actually see the dark matter, or we actually do not know what dark matter or dark energy is. But from the theory, what the theory predicts is dark energy create something called as a negative pressure, and that is the reason why we have an expanding universe. So so that we have observed. So in 2016, I think, there was like Nobel Prize was given to 3 people who discovered that we have an accelerating expansion of the universe. And so this is one of the side effects of having dark energy. So we don't actually have a strong proof as such, or we do not exactly know what dark energy is, but we are seeing evidence of it existing. So I hope that helps.
Thank you, Ragadipika. There is this interesting question for Prashant by Kanishtika. And the question is it possible that a person can travel through wormhole and reach another universe? Or is it the shortcut to travel between two universes? Prashant?
Yeah, hi. That's a very nice question because it's very speculative. Wormholes are exotic objects which are theoretically possible, and you would have thought of it as two regions of space-time which can be connected. So if you enter through one, you can exit through the other. They are of very nice interest to everyone because if these 2 points are separated by a very large distance in our universe, you can still travel from one to the other almost instantaneously. So you're seemingly traveling superluminally from one point to the other. The concept was also seen recently in the movie Interstellar, if you have seen that. However, we don't know how we can create a wormhole or how to discover a wormhole which might exist naturally. They are theoretically possible, but we haven't yet seen one. Even if we have seen one, we wouldn't know how to reach there. Gravity, as you know, tends to distort lengths by tidal forces, as Mohan had earlier explained. So there is a stretching in one direction and compression along the other direction. So if you have seen how noodles are made, you'll see that along one direction there's a stretching and there's a force which acts to compress along the other direction. So if you start moving towards a wormhole, which you might consider to be something like a black hole, you would experience these tidal forces and you would be stretched and pulled apart like spaghetti. So I hope you can survive the journey, or you can build a spaceship which can survive such a journey, but it would be extremely difficult to pull off. Thank you.
Thank you, Prashant. I'll take a couple of questions from the careers section, and I'll request Sajal to answer them. So first question is from Devesh. And Devesh asks, what are the employment opportunities we can get in India after becoming an astronomer? And the second question is from Ayush. And Ayush asks, are there any ways to join the NASA or SpaceX? Sajal?
Yes. Yeah, so I'll slowly answer this question. First is that what are the employment opportunities being an astronomer in India? So when you do PhD in astrophysics from Indian Institute or university or abroad, then you need to have some couple of years more research experience in from different institute. Then after that, directly you can join to Indian Institute or university for your, you can join, sorry, I'll show you some. Yeah, these are the institute where you can join after finishing after PhD, after 2-3 years of postdoctoral experience in research, Then you can join as a faculty member, like a reader or assistant professor or scientist. This PRL, TIFR, IUCA, NCRA, ARIS, IISc Bangalore, IIA Bangalore, RRI. So these are the institute. Every 6 months, they have a rolling application. You can give your research proposal and you can apply for the job. If they like your subject or depending on their criteria, you can join to this institute. Or apart from this joining to the institute, you can also join to university or ISER or IIT for your like a assistant professor or something. There also you can do the research. So this is the one of the question. And the second question was, you asked that how to join that. Hello, yeah. You asked that how to join NASA or SpaceX, right? So to join to the NASA, so after your masters from India or abroad, any of the from any of the country, you can look for the fellowships which NASA is offering. You can opt for that. You can do PhD there, or after PhD from different institute or university, you can directly join to the NASA. So they every 3 months they have some NASA fellowships which you have to look for that. Then you have to write a proposal. Again, depending on their selecting criteria, you can join there. Or also you can work as an engineer after your master's or bachelor in engineering subject. So depending on your background, you can opt for this career. And for SpaceX, also after master's or bachelor in engineering, you can join depending on your subject. So you have to look for when their opportunity is coming, so you can apply for that. I hope I answered.
Thank you, Sajal. I'll take this last question of our entire session, which is again by Akash Vishwanath. And Akash asks, does Indian Institute of Science offer master's or bachelor's degree in astronomy? And I'd like to answer this question. So Akash, the answer is no. ISC doesn't offer a master's or bachelor's degree in astronomy. They run a program called Joint Astronomy Program, which is a PhD program. And this is done in collaboration with a couple of more sister institutes in Bangalore, which includes Indian Institute of Astrophysics, the Isaac Center of ISRO, and then there is Raman Research Institute. And if you want to do a PhD under the Joint Astronomy Program, please check ISC's website. And you can apply through your NET or GATE scores. And I think if you have if you have a master's in physics or mathematics, or even if you're from an engineering background, you have done a bachelor's in mechanical or electrical or computer science, you can apply to this joint astronomy program. Okay. So first of all, I'd like to thank, we have come to the end of the session. I'll like to share my screen. Let's see. So first of all, I'd like to thank all the speakers, my friends and colleagues who took out time from their busy schedule and made this Let's Talk Astronomy session successful. And most importantly, thank you to all the viewers, all the students who have attended this session. And all of your questions have been very interesting, very intriguing, and we hope that we have been able to answer some of the questions, and we hope that we have been able to satisfy you in terms of your curiosity regarding astronomy and astrophysics, as well as regarding the career aspects. Now, please don't feel upset, disheartened, or discouraged if we have not been able to answer your question during these sessions. We have all your questions intact, and we will be getting back to all these questions to you through your personal email addresses, which we have. So don't feel upset about it. We'll get back to you if we have not answered them in this session. So once again, thank you for attending this session. And for any questions, suggestions, and feedbacks are important. They'll help us improve. Write to us at this email address, askastronomer@gmail.com, and you can visit our website and keep posting your questions